Hi everyone, today we'll present our work, EfficientVPR, toward efficient visual place recognition via sign-aware prompt tuning and adaptive feature enhancement. I'm Wenjing Tang, your presenter for today. Let's start with some background. Visual place recognition, or VPR, is essentially an image retrieval task. The pipeline is straightforward. Both query and database images are encoded into features, then matched to find the top one result, from which we get positional information. However, VPR faces a core dilemma, balancing three competing demands. First, robustness to environmental changes. Second, memory efficiency for large-scale databases. Third, real-time inference speed. As you see here, the same sign can look dramatically different under varying conditions. Now let's talk about some existing works. VPR methods can be simply categorized into two main streams, one-stage and two-stage methods. While two-stage methods require storing massive local features and performing geometric consistency verification or local matching, leading to substantially higher memory burden and inference delay. So we present a novel, efficient one-stage framework. We use standard V2Small as our backbone. To adapt it to VPR without adding too many parameters, we designed SignVPT, a sign-aware prompt tuning method. It only fine-tunes a small set of prompts, so the model keeps its pre-trained general knowledge but becomes discriminative to sample-specific sign characteristics. Next, for feature enhancement, we use two parallel modules. MSIA extracts multi-scale global features. Meanwhile, OLE focuses on structured local features. Now let's move on to the experimental section. Here we compared 8 single-stage methods and 3 two-stage methods. With Dino V2Small as our backbone and using relatively compact features, our method achieves a new SOTA level under the same model scale. Importantly, it even outperforms methods built on larger backbones like Dino V2 Base or Dino V2 Large. We also did cross-model comparisons at the same feature size. With same feature dimension, our model outperforms SOTA approaches based on Dino V2Small and Dino V2 Base, achieving higher accuracy on most benchmarks and the overall average. We now turn to an analysis of our method's efficiency. Compared to the two-stage SOTA method, FOL, our method achieves a reduction of 78.4% in peak GPU memory usage, 99.3% in memory footprint, and 90% in total number of parameters, while the inference speed is improved by 7.1 times, all with only a 2.5 percentage point drop in average R@1. Here is some qualitative comparison. We evaluate challenging cases and various viewpoint changes on the left side and domain shifts on the right side. In both subfigures, the green boxes indicate correct matches, while the red boxes show the errors. As you can see, existing SOTA methods often fail when the viewpoint changes dramatically or when the environment undergoes a severe domain shift, especially in cases with non-overlapping regions. In contrast, our method localizes correctly in all these hard examples. This vividly demonstrates that our method can better avoid being affected by non-overlapping regions, and thus more robust to diverse viewpoint changes and dynamic occlusions across various signs, even under dramatic domain shift. Thank you for watching. If you are interested in our work, let's chat. Our code will be available at this website.